Hello, Jordan.
Hello.
Hey. Hello, Khalid.
Yeah. Hi. How was the weekend, doctor?
It was okay. Yeah, first week. Break.
Do you still, as we do here, self-quarantine at home and so on?
Tell that again.
Do you still do the same in US as we do here, self-quarantine at home?
It is not very strict here in the sense that if you want to go out, I mean, it's a self-guided quarantine. I mean, it's not a strict imposition by the, like police will not give you a fine if you're seen outside. Put it like that.
Yeah. It was the system here. They are losing up, you know, now. If they found you outside, they would ticket you for $3,000.
$3,000.
Yeah, at some time, yeah. Wow. During the pandemic, yeah.
Oh, we had a guy from our area who sued the governor over the executive orders, and he has events. There's tons of people there. They're not wearing any masks or anything. So one of our towns got, they made national news because they had a mini prom, and like 14 of the kids have come down with positive test.
I think I've heard of that.
Well, made it into U.S. News and People magazine. You know.
Where is this? It's
Mount Carmel, Illinois.
Oh, that's not aware of
Yeah.
it. Yeah, these are tricky. Yeah.
Yeah, I think I see many people, even here in Saudi, they don't take it seriously. I've seen more people in US, they don't take it seriously, but it's a very serious issue, guys. Stay safe, please. Yesterday, actually, we lost one of our neighbors here. She was like 60 years old or something. She was struggling for some days and she passed away.
Oh.
So stay safe, guys.
Yeah, yeah. Only 2, 3, 5. So how many are there in this house? I think it's 8, I suppose, right?
Next time.
Yeah, 8. That's 8.
The
Number of students who attend.
Oh, okay.
Put together, I think it's 8. Okay. I think 3 are out there. I think, yeah. 5. Is it one? No, 3 plus, no, 3 plus 4, yeah. So if one more comes, you can account.
I was just looking for Michael. Michael is not here, so I can be here.
Oh, I see, that's all you. Oh, that's how you judge. Okay, good. Okay, let me know if I had to zoom in or anything, in case it zoomed out too much. You're not able to read, but you know. Give a homework. 1, we postponed this, right? And there's a homework 2 I decided on, but I'm not going to come here, so I don't remember. That's, yeah. So we have done pretty much 2 simple things just to summarize. We sort of motivated that the divergence of vector R over R cube is actually 0 everywhere, but it could also be tending to infinity. This is R is equal to 0. No, not equal to 0. And if this was R equal to 0. This was not very obvious, but one can expect it to be the case if it is 0 everywhere. If sum of 2 quantities comes out to be a finite quantity, so it better be infinity there. But what structure of the infinity there we don't know yet, and we will talk about that. Right. So that's one information content we can take home. One can also say in the same, while we are talking about that, this is R over R cube. We didn't explicitly evaluate this, but we just said that curl of the vector R is equal to 0. If we were to explicitly do this, this comes out literally zip. Like everywhere, this is 0. So how about this? Since we haven't really did this right away extra tip. Like we have all the tools to evaluate that. And this should be imagined, or as far as visualization goes, this should be thought of as electric field. Divergence of the electric field is usually 0, except if there is a charge sitting at that point. So the only thing you want to look for is that if you don't have a charge at any point, the divergence of the electric field has to be 0. That's Maxwell's law. Right. Similarly, there are things for the magnetic field also. We'll talk about that as we proceed later into this class today and in more detail into the semester. But all this needed, we were also trying to prepare ourselves with the vector product and vector, or the vector scalar product and vector triple, or the vector scalar product and vector, and the vector product. Yeah, no, you don't say vector scalar product and the vector product, right? So we were trying to incorporate the gradient into that. And few things, we were using the index notation, and whenever it came to a dot product, we set this is AI times BI. And as far as we don't move things around A and B, as far as the placement doesn't go, we don't move it freely, then you can generalize this for gradient operators also. So that's the idea. Here, there is a notation here that I is repeated. So it is implicitly understood that this is a sum. So this is like you have to visualize this as there is a sum. Right? You don't write this, but there is an I is equal to 1 to 3. Right. So that's how it's understood. That's index notation. In fact, you can also write this in terms of Kronecker delta. So that's AI delta ij times ej. So this is in terms of two indices, I and j, and this is Kronecker delta. So let me define this. This is Kronecker delta symbol. And that's delta ij is equal to 1 if I is equal to j, and that's equal to 0 if I is not equal to j. That's a definition, but as far as its function goes, the way it works is one thing that is useful is ij times, let's say, bj. Because of this property that it survives only when I is equal to j. So the prescription one learns is that whenever a Kronecker delta comes with another vector and its indices are common, you can just contract. This is called contraction of this index, and you simply replace this with the I. So this is equivalent to saying, so if you were to look at this more explicitly, you're saying j is equal to 1 to 3 delta ij bj will always be equal to ei. For example, if I was equal to 1, this survives only when j is equal to 1. If I was equal to 2, this survives only when j is equal to 2, and so on. So that's a way to contract, and that's the idea here that the I is the same as del ij bj. So you want to have that going. So Rob, you're familiar?
Actually, just went over that part of the lecture from Math Methods.
So you did cover this much, yeah.
Yes.
Okay. Yeah, again, I should have realized. Yeah, okay. So the same thing. So this is scalar product, and there is a cross product similarly. So we have A cross B. So what is A cross B? This is a vector. So we need to have an index for it. So that means to say it has 3 components, right? Here we didn't bother to write the index because it has only 1 component, right? The dot product has only 1 component, so it is equal to this. But here it's a vector, so there are 3 components associated with it. And the 3 components are given in terms of what is called Levi-Civita symbol. So remind this again. So this is J and B of K. Okay. So what is Levi-Civita symbol? Exactly like a Kronecker delta, these are also definitions, and these are third rank tensor, so it has 27 components, and they're mostly 0. 21 of the 27 components are 0 in Levi-Civita symbol, and this is equal to +1 if I is equal to 1, j is equal to 2, and k is equal to 3. So this means there's a notation here that I is equal to 1, j is equal to 2, k is equal to 3. If they come in that order, that's plus 1. And 2 more of them. So this is 2, 3, 1, and 3, 1, 2. Notice the cyclic order in this 1, 2, 3, 2, 3, 1, 3, 1, 2. So they are all cyclic. And in that case, that's plus 1. This is equal to minus 1 if this is not one of this, but it is, let's call it anticyclic. So this is 1, 3, 2, 3, 2, 1, and 2, 1, 3. If it's either one of these three, then it is minus 1, and it's 0 otherwise. 21 other components. This is not the whole of it, so this is only 6 of them. If these are 6 of what we have set listed, then it is plus 1 or minus 1. It is 0 otherwise. And in terms of this, the cross product can be written as a Levi-Civita product, or one can write the indices of the cross product using the Levi-Civita symbol. Question of that?
No. The otherwise is just like repeated indice.
Yes. Any of others will have a repeated index. So the yeah, that's a good point. That any other combination you can think of in this permutation, like the 27 pieces, like 3 times 3 times 3, will have either one of those index repeating. So there will be either 1 repeating or 2 repeating, or at least there will be, if not 2, it could also be 3 times. And anytime that happens, that's equal to 0. So good point that Levi-Civita symbol requires that all 3 be different. Anytime that repeats, will be 0. Based on that, a nice identity, which is very useful, is and even though we had a more general identity is available, but what we will need is whenever one of the index repeats, what we are going to very quickly, so this is the dot product and vector product, we want to compound this, in the sense build the bigger products out of this. And one of the identities that's useful is ijk, and let's say yeah, m and k. It doesn't matter which one repeats, but it should be at the same place. If the third one repeats, it should be at the same place. If it's not in the same place, then you can move things around. Use the antisymmetric property of the Levi-Civita symbol, which while we're doing this, you will see. And this is equal to I m del j n. Notice I goes with the first one, j goes with the second one, and then swap it. This is I n. That's what you want to. These are the things you will need for what we are going to do in the next half an hour. So primarily these 3 quantities. So whenever you have a dot product, you want to see that the index repeats, and if it's a cross product, it comes with a Levi-Civita symbol. So that's any questions here? Rob, have you seen Levi-Civita symbol before in some form?
I've seen it before. I've not really used it, not applied it.
Please look into the lectures. It's only in the first 2 weeks that this is spread out. After that, you can leave the lectures altogether. Yeah, it should have tried before. So for others, I realized that some of us are not in the mathematics class. So it's tricky because some of it's covered in there. I can always argue that, yeah, this is required or something, but no, it's good to have a fluency in it. So basically, I derived this, or I shouldn't say derive, I explore this in a lot more detail in those lectures. That's a good student. But these are the quantities we will use as far as user goes. Okay, so we want to see how this is used. So let's do some examples. So example, let's take a simple one to begin with. Let's say we have, let's take a triple, maybe we did this before. Did we do this before, by any chance? That's okay, so let's repeat this. Is that a scalar or a vector? Surely vector, right? I will have to ask that. It will have three components, right? Three components, I is equal to 1, 2, 3. That's the three components. And the idea is to get, if you're already familiar, this is a dash tab rule, right? But we want to be a little, like, hopefully you're familiar of this. A cross B cross C is equal to, typically this is remembered as back. Okay. It has a component along B, it has a component along C, and it has no component along A. The idea is that it is perpendicular to A, so it won't have that. So that's a way to remember it. But one has to be more careful. Notice in this, I have moved A through B. So we would like to know what if one of them was a gradient operator, right? How does this change? Is it still valid? So that's a simple question we are asking. First, let's see how this goes through, and let's be careful of not moving things around each other. Like A and B, keep it in the right order. That's all. So this is a vector product. Use this idea. This will have a, let us say it a simple I, J, K. J goes to the first vector, so that's J. And this is B cross C. So the kth component of the cross product B cross C. So that's equal to this. And now the moment you see a cross product again, do it again. I, J, K, J, and this is K, M, N. I cannot use I and J again because I've already used it. So I have to use fresh variables. So this is B, M, C, N. And these are all sort of very trivial, simple rules as to be able to use fresh variables, but for the first time when you're doing it, it might seem, oh, why do we do? These are numbers. Even if this is an operator or a matrix, whatever it is, the numbers will always commute, right? So think of this as a differential operator. This will always commute. I bring this out. This is I, J, K. This is K, M, N. That's A, J, M, C, N. I would like to use this identity, but notice that K is not in the right place, right? K is the one that is repeated. That means it is summed over. But this is not in the right place, so I would like to move it to the right. And every time I swap, so K M N is equal to epsilon MKN with a negative sign. Because of this property, the moment I swap it, this becomes a -1. So this becomes, instead of being cyclic, it becomes anticyclic. And again, if I were to move to the right, so I say -1 raised to 2. Right? So this is MN. So for every swap, I get a sign change. And if I'm doing it twice, then I get a plus sign. So I can change this in that form. So this is M and K. use the identity. This is equal to I m j n minus of I n n times a j m c. Let me go a little slow since this is the first example I'm looking at, unless I've done this before. Doesn't hurt. This is I m j m a j m n. Use the idea that whenever there's a Kronecker delta, if it comes with a vector and it is one of the indices is contracted, then you can get rid of the Kronecker delta with the change in the index of the vector. So let's think of M. So M is contracted with the M, and N here is contracted. When you're doing the second Kronecker delta, you have two choices. Either you can work with a J, you can contract it with J, or with C. C either way is okay, because it will eventually give you a dummy variable. And if it is repeated, it doesn't matter whether you call it J or M. So if you were to collapse these things, what you get is a J, M becomes I, and N becomes J. That's your relation. And the second one here, similarly, N gets contracted and M gets contracted. And you again have a J. M this is D, J, and CI. Now, if you notice that J is contracted here, that means it's a dot product, right? First of all, I is the free index, that means that's the free vector. The left-hand side, whatever is the index there, that decides what is going to be your free vector. So let me write this as AJ, vector B, and CJ. So remember, again, I should keep this, if I erase this. You remember usually as back minus. And we'll see if that is indeed the case. And this is so the free index is C. And this is AJ, EJ. Whenever an index is repeated, that means there is a dot product between them. So there is a dot product here, but there is no way you can write it with a dot, because if you were to write the dot here, it will dot it with D. So the easiest way is to just keep it as it is, with the understanding that this is dot product, right? This is a dot product. So there is a dot product between A and C. It is what it is here. But if you want to write it in that form, you have to move this around. And you may not be able to do that if this was a gradient operator. That's a point. Here again, if this was all commuting, this can go through and you can write that. And let's write that as A dot B. So that's what it is. Let's see an explicit version of it. And we'll come back and actually replace it with one of the gradient operator. So let's do a simpler one. So let's say this is L. Yeah, what if both of them were gradient operators? You can actually go through this and even immediately use this result right now. We have it. But just as a practice, I'm going to go through this few steps, but now in a relatively faster way, so I won't go through the details. So this is I. This is epsilon I j k L j and epsilon k m n L m k n. That is, you can write it down immediately. So you're already in this step. Again, it is clear that if I were to move this k 2 times, I can use the identity. So this is L I m L j n minus of L I m n. That's j m n. Again, collapse these things. M gets replaced with I. So this is L j I. It is exactly the same thing that we have here. And this is AJ minus of J. M is, oops, what did I do here? I M, I N, and this is M. J with M. So it's supposed to stop that. So M gets replaced with J, so that's J and M. AI index. Now, here we said that, oh, we cannot, I cannot move this A through B. So here we should be careful. But can I move del J, del I? Right, so the question we have is this by any chance equal? Is this equal? Whenever such a thing comes about, this has 3 times 3, 9 components, right? Evaluate each one of them and see. Check it out for the first time if that works out or not. If J was 1, I was 1, this is d by dx, d by dx. Right? So this is the matrix, right? So this is d by dx, d by dy, d by dx, d by dz. So the left hand side has the structure. So this is, and so on. So there's one here, one here. And you want to ask what happens if you were to replace them. So you very quickly realize that these are partial derivatives. And you're asking, in general, is d by dx times d by dy equal to d by dy, d by dx of, let's say, some function f. That's typically act on that. Is that the same? Is it equal? And why would it be equal? Under what conditions are they equal? Or what conditions are they not equal? The point is, can we think of a function whose which does not satisfy this?
Can you actually move the board so we can see? We
I forgot. Yeah, what I was writing here there is that d by dx of d by dy of the function f is not equal to in general, this is, I shouldn't say in general, most often that we deal with, the functions that we deal with, that's the same. But can we think of a function f where this is not satisfied? Or the question is this always true? So how about, yeah, this would be good extra credit, right? This extra, I'll give you a hint on what to look for. So find a function f for which the x derivative and y derivative are not the same. But we usually do not work with these functions because if that was the case, then that means that's a clear indication that the energy or the potential is not conservative. So what's the difference between a conservative and non-conservative force? If you remember from your, let's say,
Conservative is path independent.
path independent, or it can be integrated upon, right? So if you go from A to B, it has a unique answer. It doesn't matter how you go around, it has a unique answer. So it's path independent. So it's usually called, so you can translate it in another form, which has to say that del cross F is equal to 0, correct? And del cross F itself is energy, right? So so remember, if it is conservative force, F is equal to negative gradient of some potential, right? That's the idea. So if you remember your conservative force, if it is conservative, you can write it as a derivative of potential, only if it is conservative. If that is the case, I can say that this is del cross of u is equal to 0. Del cross del, if you were to write all the components, this will involve all this, this will, if you better, yeah, so this will involve all these properties. How to say this? Let me use indices, right? So this is epsilon I j k del j del k of u is equal to 0. That means that whenever they are not the same, it survives, so that's equal to 0. So that's that antisymmetry statement. So if it is a conservative force, which is what we are usually interested in, and whenever we are doing theory, otherwise it is almost, it becomes what happens if it is non-conservative? Yeah, that's a good point. So then things becomes irreversible. You cannot come back in the same form, and energy is dissipated. So then an analytic derivation of the quantities involved becomes hard. Like thermodynamics is a classic example where quantities are irreversible, and it is not easy to write down actual functions for example, how much heat is generated when a mechanical system happens. We cannot write a proper function for it. That's because it's an irreversible process. It is not conservative, but most of the time Maxwell's equations are conservative system, so everything obeys. So that means, or in simple words, it can be described using continuous functions. Like whether you go this way or that way, you reach the same point. So it's path. So that's good to note. So if this is the case, we will work in that regime most of the time. Then you can actually move this. So this is the derivative r. This is del j. Okay. Notice each of this gradient has to act on everything on the right hand side, right? That's our understanding. If I not return the brackets, this acts on everything on the right. this is a del square, del dotted with del, if you want. That's called a Laplacian. This operator is called a Laplacian, and there is a vector. So this is the same as gradient of the divergence of the vector field A minus the Laplacian. There's also a nice feature in this. This is again a so notice that if I were to write this as also write this del minus of del squared. And now this is a dyadic, so a dyadic in the sense that two vectors, right? So this is dotted with E. The first quantity is clearly divergence of A, and then there is a del in here. But this is not okay because this has two vectors in it, but this is a scalar. So I have to make this a dyadic. So I will introduce a unit vector, 1 in here. So if you want to see it in terms of indices, this is I, J, this is I, and then J, this is like a conic delta, and this is J. So the free index is still I.
So this is the like the wave equation.
No, not the wave equation. Wave equation requires a time, right?
Yeah, but if you replaced A with E.
No, right? Because okay, wave equation is this. If you recollect, del square minus et square of the electric field, right, is equal to 0. That's wave equation. Time derivative, and that is a speed, 1 over c squared. Right. That's a wave equation. This is so. What is this? So it's we will. This is everywhere in EN, and you will see this structure. What is that equal to? So, so let me tell a few things about it. So is that clear why it's not a wave equation? Right. See any questions on that? Yeah.
Not exactly, but I'll take your word for it for now.
Not exactly. Okay. Okay. Wave equation requires oscillations in both time and space.
Yeah, but the left-hand side of the equation would be equal.
The left-hand side of the equation.
The right-hand side would be minus d by dt mu naught times the current density plus.
Yeah, but then you have this extra piece there. Right? What happens is that, okay, if A was, okay, maybe that's what you're saying. If A was the electric field, then you have del dotted with E coming in, which is 0 using Maxwell's equation, if there were no charges around. Right?
Yeah.
And the first term goes to 0, and then this is what contributes to the waving. Right.
Well, del dotted with E, if you restricted your.
What is del dotted with E in general? It is rho, right?
Rho over epsilon naught, yeah.
So that's not 0 in general on the left, the first term. But if you were in a region where there is no charge, it doesn't mean that it's an approximation.
Yeah, if it's equal to if it's equal to 0, then your J's and P's will be 0.
That's correct. Then it leads to, I mean, or at least it gives you one term in the wave equation. Probably that's what you have in mind. So I agree. Yeah. Okay, helps.
Yeah.
Okay. But as of now, it's very general. And so let's yeah, so how do we motivate, what kind of operator is this? So let's think of, yeah, so usually, I think, okay, so I'm going to, if you are in rectangular coordinates, it turns out that you have I hat plus j hat plus k hat. It turns out that these 3 unit vectors will always, notice that it's no dot product here. No dot product, no cross product. This is 2 vectors sitting adjacent to each other. So it's, in a sense, it's a dyadic form. Like in these kind of situations, we call it dyadic. So this are 3 unit vectors. If you place them like that, if you evaluate that, will always give you the dyadic or the unit dyadic. You can take any 3 orthogonal unit vectors and it will always be the case. So for example, in spherical polar coordinates, this will be equal to r hat, theta hat plus phi hat. And that's equal to, like in cylindrical coordinates, this will be rho hat plus whatever, phi hat plus z hat. So these are the rectangular coordinates. I haven't done this in either of the classes, but hopefully within 3-4 weeks it will get convincing to you that this is the case. But if this is the situation, so that means to say that in general, I can always say, in general, given any 3 orthogonal coordinates, this is always any 3, and this could be position dependent. What can we say about, or maybe, yeah, so, yeah, let me put it this way. So just to give you a feel for this, let's take a vector A, doesn't have to be this. There is a vector M, and I want to see its components in any one of those coordinate systems, for that matter, even in very general coordinate systems. So let's have a feel for it using this rectangular coordinates. What I would do is, I'm interested in its components. Notice how it works. I write dotted with 1, which should be perfectly fine because I just multiplied by 1. But that's, if I now use a representation for 1, is this I hat plus j hat plus k hat. And now change the quantity. You say that this is m dotted with I in the I hat direction plus m dotted with j in the j hat direction. Is this visible to you guys?
Yeah.
Plus m dotted with k in the k hat direction. And now this has a meaning. Now you say that these are the components, right? So what is this doing? These 3 unit vectors are projecting this vector along its direction. See the interpretation here. M dotted with I in the direction of I. M dotted with j in the direction of j. M dotted with k in the direction of k. And the same thing can be done for each one of this, any arbitrary coordinate system. In this sense, this is a completeness statement of your space, of your vector space, if you want. In quantum mechanics, you deal with infinite dimensional vector spaces, but these are finite dimensional, 3-dimensional vectors.
Can you expand on why it's called completeness? Like, does it
means
give more information somehow?
Yes, so the completeness is that any vector can be written in terms of these three vectors. For example, let's say, an example could be, let's say my space is a two-dimensional space. It's the same unit vector, but now it's 2. Let me say this is 2 by 2 plus j hat, right? That's incomplete for a three-dimensional space. Agreed? So if a vector A is three-dimensional, then we know just visually that, oh, you can always think of a vector which cannot be projected into these two. So completeness means that think of any vector in that particular space, and you can write that in terms of its, or there exists a representation in terms of those three unit vectors. So in 3 dimensions, you need only 3 of them. If you're having 4 dimensions, you need 4 of them. In 3 dimensions, it's kind of a trivial statement, but now what happens is that in quantum mechanics, you are usually working with infinite dimensional spaces. And then it is not very clear whether you have covered everything or not, because there are lots of kinds of infinities. So when you're having 1, 2, 3, 4, 5, 6 is also an infinity. Like a classic example is, what is this? 1, 2, 3, 4, and so on, right? That's all the numbers, let's say, and that is another space. 1, 2, 3, 4, right? So this is one. So you have a set which has elements which can be labeled to 1, 2, 3, 4, and so on. There is another set which can be labeled to 0, 1, 2, 3, and so on. And then you ask which one has more number of entities, let's say. Which one has more? That's a question.
Well, 0, 1, 2, 3, 4.
It seems like. Anyone else want to add on to it?
I mean, yes, one would think that the 0, 1 would be larger by, but it's only larger by one number, which at the scale of infinity is, they're like the same infinity.
Yeah, but the way you stated it, I would disagree. But the answer is correct that this is both are the same set.
Those are, about the same set.
Or same number of elements in it. If you were to count them, they're the same. Now the question is, how do you count an infinite set? Right? So the only way to count is, what do we mean by counting in an infinite set is that, so these are the elements, let's say. So these are all elements.
Well, if you subtracted them from each other, you'd get the same thing. That's true.
Subtract them. No, let's say this was 5. How about that? If you want to subtract them.
Okay.
Right?
Okay.
Or give it some -1. How about that? If you don't want to repeat, right? So it's -1. Still, it is the same. For that matter, let's say rational numbers, right? P over Q. So rational number, all of us can imagine rational numbers, right? Rational numbers versus this, like these are natural numbers, right? Which one is bigger? Now it will, you'll be very confident that no, rational number has to be bigger. That's it. Then set that. How can this be smaller or equal to the natural number? But the statement is no, it is the same. The number of entities in the natural number is exactly the same as a number of entities in the rational.
Only when you go to infinity, though, right? Only at infinity, but you have to go all the way to infinity.
So let me state it more clearly. Okay, so this is all.
That's how you get that -12 crap from string theory.
This is not that. But and that's not. So let me convince you guys. So this is the context in which we are talking. Okay. So what does it mean to say countable set? What is it means, so we are trying to
1
count.
plus 2 plus 3 plus 4 equals.
Yeah, so let's say there are entities here, right? So this is, these are all some objects in a set. As far as I can do this, 1, 2, 3, 4, if I can come up with a rule, right? I'm good, that's counting. Okay, so here is how this number is the same. So this is a whole number set, 0, 1, 2, 3. So I just need a rule. So I will say that any number, map it onto the next number. That's a rule I have generated, right? So this is 2. That's 3. And I can keep going. I'll never end. So I will always have numbers available to me. There's no end in the infinite, in the natural number system. And that's the key to that. If this was finite, then I'm stuck. Then it is not the same. If you go all the way to infinity, since we'll never reach that, I'll be good. I will always have available numbers to me that I can put the labels on. That's okay. This probably is okay. Then you would say this is a trivial, probably. It's just a, I'm probably trying to use some tricks there. So let's do a more elaborate one. Rational numbers, right? How will I map it for a rational number? So remember, rational numbers can be written in the form P over Q, right? Like where P is a integer, P and Q both are integers. So here is how you can, one of the ways you can map it. So let's plot P here and Q there. These are integers, so these are all points, right? So this is 1, 2, 3, 4, and there is 0 there, and the same thing there. So every point in this way of representing it and extend it here. Right? Every point in this plane, in this discrete plane, represents a rational number. This might be slightly more in the sense that these are not proper rational numbers. What is that called? Proper fraction and improper fraction. Some of them will actually collapse, right? For example, 6 over 3 is the same as 2 over 1, right? So there's a repetition in that, but still you're only adding on numbers. So it doesn't bother you too much because you're only adding, and still you can. So we just have to show that there is a map. So here is a map. So simple. There are many ways you can think of. So you start from here, go there, and go here. That's a map. Is that clear what I'm doing? And I can keep going there. There's a rule I can generate that, oh, okay, take this, and you're in that line. And I can keep doing that. If you don't like the idea that I've done it only for one quadrant, do it this way, right? So start from here, go there, go here, go here. Then once you reach here, then you jump into the next one. So you can always make that rule. Yes, Rob.
Don't we have the limitation that Q can't be 0?
Yes, so that's so Q cannot be 0. So get rid of that point. Or where is Q? Q is on this, right? Yeah, it is a limitation. Yes. But again, it is you're only removing points, right? So I was going for the idea that this is actually finite. So you'll be good with that. So try to think about it. It will work out. Okay? Like I'm not clearly seeing what the. Like, are you worried that in that if you take care of that, then you won't be able to map this?
Oh, I wasn't worried about.
Or maybe I didn't point it out. Maybe that's that's correct.
It was left out there.
Yeah, Q cannot be there. Right? Q cannot be there. So in this line, so it's in a sense there's a dot here, right? You have to jump that point in there. So and this is a definition of a countable set in mathematics. That's well stated. So what I was trying to point out, why did I reach there? is that the question was, what is a completeness statement? In 3 dimensions, it is usually very, right away you see the space and you know that, oh, there has to be 3 unit vectors. But now let's say you're in quantum mechanics where you're working with infinite dimensional vector spaces. So that means you have to come up with infinite unit vectors, which is what we do in, like if you were to think of the hydrogen atom problem or a harmonic oscillator problem, there are infinite unit vectors there. Now, you're not very sure, have I captured all the unit vectors or not? Because this is also infinite, this is also infinite. How do I know that I have actually captured all of them? And in that case, you have to actually show that given any function can be expanded in terms of the unit vectors that you have. So that's that expansion. Given any vector m, you can write it in terms of that. That's usually a harder problem. If I were to ask you to prove that this is not valid, a counterexample is good enough. But if I were to ask you to show that this is actually valid for all examples, you have to keep trying that. So you have to come up with a very general proof for that. So completeness relation often in elementary introduction to quantum mechanics we skip, or we often assume that this is a complete set. But in principle, it is worked out in detail in another context somewhere else. Or usually we leave it to the mathematicians. Yeah, they will take care of it. But that's not necessarily one. If you're the first one to encounter it, you have to prove that it is complete. It's complete, and only then you can proceed. Does that help with the question of why is it called completeness statement?
Yes, that helps.
Yeah. So, yeah, look it up. So, why did I bring all this up? So, I was talking about this identity here, and I was trying to give some physics. That is with this. Okay. So I can write this equation in the form, this statement. This is, if you allow me to at least, notice that this has the following structure: I del j divided by del square, whatever it means to divide by a gradient operator or Laplace. That's meaningless in a sense. You don't divide by a derivative operator. But whatever that is, if you were to operate it, if you can imagine that, this is 1. And this is gradient, which is this is square times 8. That's what this means. This dot product. So what is this equal to? Let's come back in here. If this is the case, if I were to write this minus I with I, what is the right hand side equal to? This is a unit dyadic in a smaller space. So if I were to subtract one set of unit vectors, I have actually collapsed my space by 1 dimension. So this way, this is called a projection operator. If I were to take a vector A, any vector A, and multiply that by I hat I will get its component in the smaller space, right? 1 space down or 1 dimension down. So in that sense, this is called a projection operator. Like again in quantum mechanics, you see this. You define it very well, but there it is from an infinite dimensional space to another infinite dimensional space. Now look at this. There is 1 minus of 2 similar unit vectors. So this is a projection operator. And in E&M, where do you say, why do you have projection operators? That is that if you have a wave, electromagnetic wave, what Jordan was pointing out. So this is the direction of propagation. The electric field is always perpendicular to the direction of propagation. Right? And magnetic field is always perpendicular to the direction of propagation. Right? So this is always perpendicular to K. That's because of this quantity. That's an example where everything happens in a plane. But that plane could be changing. Right? It doesn't have to be all like this. K could change. Like a ray, as you enter into a medium, this can actually move. This can bend. But this will always stay perpendicular to the direction of propagation. And that's because of this statement. That's what the content of that equation is. It's not very obvious right away, but hopefully with these ideas, you can at least, I have at least motivated to a certain extent. Again, we will see these things later in more detail. Okay, so that's one identity. Let's do another identity, do some examples. So let's say dotted with A cross B. Is that a scalar or a vector? Is that a scalar quantity or a vector quantity? A scalar.
Scalar,
Yeah. Scalar. Yes. So since it's a scalar, so immediately, so this is del I and A cross B. So this is, and remember that our idea is that whenever I leave the gradient operator open without any brackets, it's understood that it is going to operate. It is going to operate on everything on the right side. Anything that follows it has to act on that. So these brackets are for the vector. So I need to have a bracket for gradient also, but now we will have the notation that it acts on everything that it encounters on the right side. Expand this out again. This is I epsilon I j k a j b k, and we're expecting that A and B are position dependent, so its derivative exists, and this is equal to I j k. This can come out because these are numbers, and del I A j b k. Again, by our understanding that it acts on everything on the right, it has to act on both A and B. So if I were to introduce brackets to clarify that, so that's what that is. I don't need to write the brackets parentheses, but that's what it is. Now I can expand it out. That is, this is where if this gradient operator was a vector, you wouldn't proceed beyond that. But now I can split this further by distributing this derivative. I j k, and I can write this as del I a j. But now I have to put these parentheses is important because this is stating that this derivative does not go beyond this point. This acts on that. That's b of k. But now I can distribute it. It can hit on b also. This is aj del I k. Here I've distributed my derivative operator. And then now let's see what this is. This is now I, j, and k. This is a cross product, right? Whenever this comes out in cross product, I can move this k to the left, and I can identify this as a cross product. So this is del cross with A, and it's a kth component. And that's P of k. This is also a dot product, but now this is ik, so I have to move only j once, right? If I have to move j to the left, so that I can identify this as ik, this is actually a cross product, but only with a movement of 1. So I get a negative sign. Notice it would have been hard to capture the negative sign otherwise. So the index notation brings it out very easily. So this is j, and this is del cross b, and this is the jth component. Make sure very clear why that negative sign comes in and why this is the jth component. So the j should be in the front. Now these are dot products. So this is del cross A dotted with B. This could be vector fields minus of A dotted with del cross B. We haven't moved A and B beyond this gradient operator at all. No, only the gradient operator has moved around the position of A and B. Does not. For that matter, A and B could be matrices here, and that's perfectly fine. So that's a vector identity you have from this. So these are the examples you have in your homework. Let's do one long one where this is a triple product. So you could do del cross with A cross B. That's a vector, so it has ith component. Based on what we have done earlier, we did A, B, and C. Right. As far as I don't move my, let's just do it again. This is I, J, K, del J, and A crossed with B. Okay. Understanding is that J, the gradient operator acts on everything on the right side. So that's I, J, K, epsilon K, M, N, J, J, M, E, N. Again, the gradient operator acts on both. Distribute or expand this using our identity. So that's one distribution, but this distribution is because of the vector product.
So you just did that without technically combining or making your epsilon symmetric?
Yeah, so in principle, I should have gone, you're saying, oh, first I should have done this, correct?
Mm-hmm.
Yeah, but I did just in 2 steps because we have done this 3 times. And that is how you will also realize that once with some experience, you can jump steps, right? You could have written this directly here, right? And then you realize that, oh, I don't have to move this K as far as these 2 things, 2 steps away. I don't have to do that all the time. So those are the steps. But now notice, if it was a vector product, this is the only distribution that comes. If there is a gradient sitting here, there is an additional distribution because of the derivative. So this is now the En plus. Oops. M del J. Earlier, I would have got this one would have split into 2, but now this splits into 4, 2 here, 2 here. There is a distribution because of the derivative operator. there is a distribution because of the vector triple product. So totally there are 4 terms. Right? That's I think this was mentioned once by Jordan in the first class or something, that we expect it to have 4 terms, and those are the 4 terms. And now we can collapse these things. Notice m gets collapsed to I, n gets collapsed to j. So in each of these terms, so I'm doing this with this. So this is j, a, I, and n gets replaced with j. So it's j. This with this term, m gets replaced with I. So the I, double j, j. And then comes the 2 negative quantities. So this is del j. M gets replaced with j, j, and bi minus of j, del j, and bn is bi. Is that clear how we've done this a few times, should have got clear. And now I had to rewrite this in terms of vectors. If A is a free vector, right? So I have to, this is del j vector A, and this is B plus vector A and del dotted with B, del dotted with B. This is minus of del dotted with A. This is vector B, and minus of A dotted with del B. Notice the last term in particular. This is not, the gradient operator is not acting on the vector or a vector product or scalar product. This is a tensor. A is acting on the, so this is a different entity of that. This term here, if it was, for example, A and B do not commute, then you cannot proceed. But we work with electric field and magnetic field. Unless you're doing quantum electrodynamics, we are going to be doing electrodynamics. And electric field components commute with each other. So these are classical numbers, right? Electric field is not non-commuting variables. But in quantum electrodynamics, there's a difference. Then you cannot do this step. But if they commute, right, A and B commute, A can commute with B, then this can come to the other side, and then I would say this is B dotted with del A. So this step is allowed only if you are in classical electrodynamics, which is what we will do. And the first and the last term have very similar forms with A and B swap, and the second and third terms have very similar forms with A and B swap. So that's a vector identity related.
So in quantum, they have the commutator relation. So you
Yes, and that's exactly. Then you will have an extra term in there when you do this, and that gives you new physics. That's a primary difference between classical and quantum mechanics. Yes, exactly. Especially like the first thing one encounters is the harmonic oscillator, right? If you do this, when you replace this momentum and the position operator, you get a new term, and that has physical consequences. So that's quantum mechanics. That's the essence of quantum mechanics. So that's uncertainty relation. Because like X dotted with T, this is not 0, right? I don't know. Right? All of us know what the symbol means, right? So I see that. So this is I H bar, but now these are vectors, so I need to put this 1 there. Right? If you want to see it in this language, your uncertainty relationship will read like this. Two vectors, no dot product, no cross product. There's a 1 there. Usually you will write this in this form. This is how it is typically written, but in this language it will read like that. So you will say this is there. That's an index notation, that's a tag form of correlation. So every time you do this swapping, you gain this extra term, which has H bar in it, which has quantum mechanics in it. Anything that depends on this term, that's a pure quantum effect. So the idea is to figure out which physics has that contribution. Most of what we see is classical. We want to see what is pure H bar. So that's a nice thing about coming. But we are going to be doing classical. No H bar in this whole course, right? H bar is equal to 0. So that gives you a feel. You should now be fine with all the homework. I think actually I did one of the 2 of them. No, 3 of them. Okay.
So real quick, the last one you did, it's incorrect to say like the gradient of A dot B.
Gradient of A dot B this way. This is okay. Yeah, this is fine. What's the point?
No, it's like the gradient of A, and then the gradient of A is dotted with B, not A dot B times the gradient.
Gradient of A dotted with B. Yes, this is different from, so what I was highlighting there is that this is different from this. Like usually we are used to either working with a curl or a dot, right?
Mm-hmm.
Either we have a curl or a dot. This is a new entity altogether. Notice. This is a dyadic, like a gradient operating on a vector in the dyadic structure. Right? This is a full-fledged. This is before it gets a dot or a cross. And then you project it on the B on the left side. You could have projected this on the right hand side also. Those are different entities altogether.
Mm.
As a dyadic, I think that's the new thing.
Okay.
Really see that as a dyadic, not as a dot product, not as a cross product. Think of it as a dyadic structure. Eventually, we do dot it, so that's okay. But this is not the same. Again, think of it as projection operator. That's. And I'm not trying to say that it's very straightforward. You have a very clear visual picture, but yeah. And remember again that gradient operator is a surface, right? Function minus a constant, right? A surface, then it is constant surface. Right? So that's what this means. So this has 3 components. Each one of them, it is actually doing that. And for each component, it is doing that. So there are constant surfaces. So one can visualize to a certain extent, but mostly this is sufficient. At least I work with this much, and that is itself sufficient. And the 2 other things you will need for ENM is that the divergence. When is that? What does it mean to have a divergence of a vector field and a curl of a vector field? Those are the primary 2 things we'll be using. Okay, let me stop here. Already 5 minutes crossed. Any comments or questions?
Yeah, I have a question, but it's not with the class. It's just something else.
So you want private? I thought it was not obvious. So what do you mean? You want to mention it or?
Yeah, I can mention it. It just has to do with the series stuff that you were talking about before.
Yeah, you're not satisfied. Yeah, go ahead.
So say you had a series, you know, the 1, 2, 3, 4, 5, 6, and you call the series something like, S, series S.
Yeah.
And then you multiply that series by the 4. We're talking about the negative 1/12 stuff.
Yeah.
You multiply the series by 4, and you arbitrarily shift that series below your S series. So now you have S, which is 1, 2, 3, 4, and then 4S, which is 4, 8, 12. And you shift it such that you can subtract the 2 and get a negative on every other term. The part that I don't understand is why in that series, the second series 4S, that it's not 0 plus 4 plus 0 plus 8 plus 0 plus 12.
So let me put it this way. Okay, so I think this will clarify it. Whatever you work with on series, it is all clean and unambiguous as far as the series is convergent. Okay? So if the series is, for example, 1 plus 1 by 2 plus 1 by 4 plus 1 by 8, so on, it gets smaller and smaller. That's a convergent series. Okay? But the series that you're talking about is divergent. And it is divergent, it is meaningless. Okay, let me begin with that statement. So 1 plus 2 plus 3, all the way going to minus 1 over 12 cannot be true. Okay? That's for sure, that cannot be true. But then why do we say that? And I didn't complete my statement. So now listen to the whole thing. Now the key is that using this, you can define a function called the Riemann zeta function, which for special cases leads to this series. Okay? But that function has to be valid and well-defined for that series. So what you do is, you start with the series and jump into what is called the Riemann zeta function. Riemann zeta function is well-defined in the whole complex plane. But that doesn't mean that this series is well-defined. 1 plus 2 plus 3 on the left-hand side is not correct, but it has a meaning when you interpret it as a Riemann zeta function. In that case, it is okay. So what you do is you're going into a bigger space. You jump from 1 plus 2 plus 3 and jump into a bigger space. And then you do some tricks there, and then you come back onto the right-hand side. That coming back is not allowed. But having said that, this is the context in which people are talking about. When you say 1 plus 2 plus 3 is minus 1 over 2, Riemann zeta function is very well defined at that value. So in that sense, it is okay. Did I roughly, so look up Riemann zeta, or when is, for example, what is minus 1 factorial? If I were to ask you, or half a factorial. Is that a well-defined quantity? Half a factorial?
Factorial.
Half a factorial, what does it mean to say half a factorial? Like 1 factorial exists, 2 factorial exists, we all learn it, right? What does it mean to say half a factorial? Half a factorial is still better. You can even define minus half a factorial.
So would half a factorial still be 1?
No, it is square root of pi.
Okay.
Okay, that's because it is gamma function. Okay.
Okay.
Gamma function for integer values or positive, the whole number values is exactly the factorial function. But now if you go ahead and say that, oh, that means that half a factorial is well defined because gamma function is well defined for half a factorial. That's not correct, because factorial functions is not defined for half. But you loosely say that, oh, gamma function is the same, so it is okay to say half. So look up gamma function and half a factorial. Okay?
Okay.
That's very easy to understand.
Yeah. Because I guess when you do all this sort of stuff, the part that I didn't understand is that you have an infinite series, but you're manipulating it like it's a finite series. So that seems like you can't do that.
There is always a catch in there. Like, it's a very subtle in the sense that you are going from one space to the other. You can always catch it. But having said that, it is, if you know what you're doing, then it is okay. You will always be able to prove a statement that you work in this form by going into the actual Riemann zeta function and doing the same thing. So
Okay.
if you're very careful, it's okay. The results are often correct. Okay, so I'm not saying that it is wrong to say it is -1/12, but I'm saying that is a details in there which is very.
So that's that negative zeta of -1. That's the -1 thing?
That's correct. That's exactly what it is. Zeta of Riemann zeta function of -1 is actually -1/12. That's a well-defined thing. That's perfectly correct. But to say that 1 + 2 + 3 in the naive form is -1/12 is a stretch. But people understand that it is a stretch, and that is the context in which they talk about. So I'm saying it's right and wrong.
Because it seems like you could get anything with the original series if you chose to just arbitrarily multiply or divide or subtract until you got what you wanted. That's what bothered me with just.
That's correct. That's what I mean by one has to be very careful. By doing this, there are rules that you have to obey, and one has to be careful that you're not breaking those rules. Yeah, you're right that it is. That's what I meant by saying it's very error prone in the hands of those who don't know what they're doing.
Like me.
It's error prone, but at the same time, people use it in the form that you're talking about. People use it.
Yeah.
Else?
So basically, I need to just go try to prove it with the zeta function, and then be satisfied. Okay.
I'll recommend going with gamma function first because that's an easier function. Like it's more well defined or more understood. There are more identities available for gamma function than. So, but the techniques remain the same. Maybe we'll. I don't think I usually do it. Gamma function and zeta function, but that's a natural thing to do in the complex numbers that we do in math methods. But I never done it. Usually, I cannot cover stuff. Also, there's this very strong suggestion that I can. It will be at the sacrifice of something else, right? You'll be giving up differential equations, which is more important. We'll see. Try to at least mention.
But is it though?
Say that again? Oh, is differentially
really that more important? Because it seems like something they use. And
yeah, maybe importance is all contextual, right? You encounter it more, maybe.
Like you take a lot of differential equations courses over their history and.
True.
Never.
Okay, how about this? I'll introduce gamma function. Or it's not just introducing gamma function. You have to introduce analytic continuation of gamma function. That's what this is all about.
Okay.
You have to talk about analytic continuation of gamma function. So let me see if I can, or maybe at the end of the semester, how about that? So I'll go around with complex numbers and then maybe at the end, last week or so, last two lectures, I think. I always wanted to teach it, but I never end up doing it. Analytic continuation is a nice concept. And you don't learn it often, not in graduate school, you never see it. Only in some advanced courses you come to see it. But okay, I should stop. 15 minutes. Sorry. Blame it on Jordan.
Yeah,
but yeah, he said it before. Hopefully it was useful.
I do have a question about that last step where you're saying A and B are
commute. So
yeah. No, and I understand that. But that first term, would you? I think you kind of addressed this already, but it doesn't make sense to try to dot B with del before treating del and A as a dyadic.
It's okay to you can either do dot first or operations first. Keep the structure as it is. That's all.
Okay.
So you can do dot first or the derivative first. That's okay. Order doesn't matter.
Okay.
But it has to do both. It has to act on A and it has to dot with. Acting as a derivative, when it comes to its derivative property, it is acting on A.
Yeah,
When it comes to its vector property, it is acting on B.
okay.
That's the way to
Oh, okay. Yeah, that makes sense.
Okay, thank you. Michael, Alia, was it okay?
Yes,
Yeah.
sir. Thank you so much.
Very
Okay.
And then is there some identity to get the last statement back to a cross product that there's an identity?
Cross product here.
Like on the homework, it's,
Oh, is it not in that form? Oh, what? Oh, so I didn't finish it. That's good. So, no, there is no identity. What I would suggest is that there are 4 such things. Do all 4 and then add them up. You see what I'm saying? There is del of A cross B, there is del of B cross A, I guess, or A cross C, and so on.
yeah.
And get the left hand side there, and right hand side will all cancel out in this.
Okay, with the dot products.
Yeah, try it out. I mean, or do your own. Yeah, that's a homework problem. Figure it out.
Yeah, they cancel each other.
Yeah. Okay, good. Okay, thank you. Sorry again for extending. Shall I disconnect? Jordan, Michael, Alia? Okay, bye-bye.
Bye.
Bye.
Control 5.